Yes, so recording has started. So welcome once again. So this is today is the fifth and sixth because we have a 2 hours class today, right? A brief recap of yesterday's class. We have started our discussion from this inverter with resistive load. We have tried to solve one small problem, and we have seen that to implement a resistance of 205 kilo ohm, 205 kilo ohm, which we have found from our last one of our last example, right? That we need 205 kilo ohm in order to make the power dissipation minimize, right? And we have seen that to implement that resistance by using the diffuse resistance technology, we need a length of 10.25 mm, right? Resistance length. Sorry, which is practically impossible in case of VLSI technology. So that's what we have tried to implement. We try to see that if we can replace this resistance, right, by a MOSFET, because MOSFET takes literally very less space in VLSI, means on a chip, right? So that's what we have connected one MOSFET in this configuration, which is just shorted the gate and drain. And basically, then this MOSFET will behave as a type of an load and with the characteristics like this. And from here, we have seen like how to find the VTC. And we have seen that also in which region the transistors are operating in which mode, right? For example, in the linear, whether the transistors are in the linear region, in the saturation region. These things are in the cutoff. Those things we have discussed, and from here we have derived this VTC. And also, it is not difficult to find what would be the equations from here, because when this V in would be less than this threshold voltage, then we have seen what will be the expression of this V out. If it is greater than VTH, then what would be this V out? So similarly, this for like different sections, for example, this or this, so we can explicitly find the equations, okay, of these straight lines, means the relation between V out and V in. That's basically the line, right? So we can explicitly find these things, right? And that's actually what we have discussed yesterday, right? Then we have also seen, also given discussed about one homework where you need to find couple of things. One of the things, the static power dissipation. So it is important. So far, the two inverter techniques or technology that we have discussed, in both cases, we have seen there are static power dissipation is the issue. So what do you mean by static power dissipation? Static power dissipation is when this inverters are in a static state. What do you mean by static state? Means suppose if you have given logic 0 at the input and keep it. You are not changing the input from 0 to 1 or from 1 to 0. So either you have given it at 0 or you have kept it at 1, right? Then if there is any power dissipation, then that power dissipation is called the static power dissipation, right? If there is no such power dissipation, then it is called the no static power dissipation, right? For example, you can see it here. When if you have given V in equal to 0, this transistor is off. So this V in is not in touch with this ground. So there is no connection between V out and between this VDD and ground. So no power dissipation from the battery or this source, right? So when this V in equal to 0, static power dissipation is 0. But when you have given at logic 1, means suppose say 3 volt, say the VDD is equal to 3 volt, then logic 1 means 3 volt, right? I'm saying that is close to 3 volt, right? Because at the beginning itself, we have seen that in digital, if you say logic 1, it does not mean exactly 3 volt. It's a actually range of voltage, right? So it's some voltage close to this 3 volt. So obviously this 3 volt make this transistor on, right? Then you have a direct connection, you see, through this load, okay, through this both this transistor, there is a connection between VDD and ground. So there will be a current, means that one ID current will be always flowing from this VDD to this ground. So as long as this V in is at logic 1, it will dissipate power. So you can clearly see here, then static power dissipation is there for this type of inverter, right? So we need to solve that, right? And the other issue was also here. For example, if you look into this VTC, so we have seen here the VOH dash is actually one threshold voltage below that of this supply voltage, right? And also this VOL dash, that is not equal to 0. So both the highest output and the lowest, I mean the maximum and minimum output are not equal to the rail voltages. So that is also another disadvantage. Why this is a disadvantage? So I don't want to discuss all these things right now, because then it will be confusing for you. But in the later stages, you will see that even for CMOS cases, in some cases we will encounter this type of phenomenon, that okay, when the output voltage is becoming some lower than the drain than the rail voltages. And there you will understand why it is very important that the output voltage is should be as close as possible to that of this rail voltages. Right. So we have also identified the issues in this particular type of design. Right. This diagram is regarding one of your friend's doubt. So again, anyway, today we are going to take this part and discuss it more. Right. So for today's class, we are introducing one more type of inverter, which is called this NMOS inverter with depletion load. So previously what we have done is the enhancement mode. Now what we are doing with this depletion mode. So depletion mode means okay. So far the transistor that you have learned about this MOSFETs, they are the enhancement mode transistors, or normally off transistor, or in short it is also called E mode transistors. Right. So if you see the construction of an basic transistor, is basically something look like this, right? It is a P silicon. I am considering this NMOS, right? So it is a P silicon. Source and drain sides are doped with N plus N plus. Then you have this oxide layer on top of this either polysilicon or the metal layer. So that forms the gate. So it is gate, source, drain, and this is P silicon, right? So here you apply a positive voltage. Let me say that when you have applied Vg equal to 0, then there is no channel, right? Because it is N type, this is P type. So no current can flow from source to drain. Channel does not exist here, right? So this transistor is off. So when Vg is equal to 0, ID is equal to 0, right? No current. However, now you increase it to say 1 volt, and say the threshold voltage of this transistor is 0.5 volt. So that means if the gate voltage is above 0.5 volt, then one channel will be formed here. That this channel is formed here by inversion, right? So that means electrons will come here and form this channel, right? Because it is NMOS, right? So you apply a positive voltage and the electron channel will be formed, and that basically connects this source and drain. You have a connection between these two, and you have a finite value of current, ID. Now, as you keep on increase this Vg, the current will keep on increase, right? So I am assuming that you have kept Vd at constant value, right? So one thing you have clearly seen, that when you have applied Vg equal to 0, that means no voltage applied. So the transistor is off, in a off state. So that is referred as this normally off condition. Means when no gate voltage has been applied, how the transistor is behaving. So it is normally off behavior. Okay. But now you see for this case. Okay. For this type of transistor. For this type of transistor here, what we have done, only a small change, that is between this N plus N plus. So exactly same thing, right? But here what we are doing, we are saying that this region we have intentionally doped with N type. So then for this transistor, see, even if you apply gate voltage now equal to 0, then what is happening? Between source, which is of N plus, and drain, which is also N plus, you have an N channel. So electron does already exist in this channel, right? So that means at Vg equal to 0, there is a path from source to drain, current can conduct. So this type of transistor, as when no gate voltage apply, it can conduct. So it is called the normally on. Means by default it is on, right? So these are called the normally on devices, right? Now, what we have to do in order to turn off this transistor? Okay, now say apply -1 volt, right? So when you apply -1 volt, then what will happen? You are applying -1, so that will basically try to pull this electron, or try to repel the electrons closer to this interface towards this side, right? That makes a depletion layer here, right? So that forms here depletion layer. So the depletion layer means this region does not have any electron or hole, no carriers, right? So this region cannot participate in current conduction. But remember, earlier you have this total region which can conduct current, right? Now you have reduced the channel thickness, so obviously will current will decrease, right? Now further, if you increase this gate voltage, say Vg equal to minus 2 volt, then this depletion region will further extend, right? And that basically your shrinks your channel thickness. That means your current will further reduce, right? Like that, say at a particular voltage, say at Vg equal to say minus 3 volt, okay, it is say this depletion layer touches this layer, right? So at that moment, there is no path for the current to flow because the entire channel has been now been depleted, right? So by applying a sufficient negative voltage, you can deplete this channel, right? And make the conduction stop, right? So this type of devices are called this depletion mode or D mode MOSFET, right? Or sometimes it is also called as normally on MOSFET, right? So I hope this part is clear, like from the construction wise and from the operation point of view, how this enhancement mode and depletion mode devices are different and why they are called this normally on device, normally off device, that is the enhancement mode devices, and why these demode devices are called this normally on device. So any doubt? Any doubt? Okay. If there is no doubt, then let us move to the next part, which is regarding the circuit symbol, right? So for normal MOSFET, you know the circuit symbol is like this, right? For NMOS. For NMOS, the circuit symbol for this type of depletion mode MOSFET is represented in this way. This part is again the same as that of this enhancement mode or E mode MOSFET. Only thing is that to represent that the channel does already exist, okay, even before no gate voltage has been applied, so we indicate this by a thicker line here. So this indicates the channel, indicate the existing channel, right? Okay, so if this part is clear to you, then we are not discussing anymore what will be the IDVD characteristics for this type of MOSFET E mode. We have done it in this course also a couple of times. Now let us focus on this. Okay, let us focus on this demo device. So, and obviously it's a MOSFET, so its IDVD characteristics also expected to be like this. And say for this MOSFET, the threshold voltage is minus 3.5 volt. Okay. Now, please guide me. What could be the probable voltage for this one? Gate voltage for this?
Close to minus 3.5.
Close to minus 3. Yeah, it is actually minus 3 means the threshold, so there will be no current. So it is basically little bit more positive than minus 3.5, right? So let us say minus 3. Is it possible minus 3? Aniket?
Yes, sir.
Minus 3 possible. Okay. So VGS equal to minus 3. So that is possible here. Okay. No issue. So then is it possible this is minus 2.5? Minus 2, minus 1.5, minus 1, minus 0.5. And if you want to take it one more, so probably you can take one more here and say like this is for gate voltage equal to 0. Any doubt? No doubt, right? So it would be like this. So for gate voltage 0, the ID VDS characteristics would look something like this, right? Okay. So I hope now this E-mode part is clear to you. So we would be able to take this D-mode device from this point onwards and make a circuit and make this D-mode device use this demo device in one of our circuit, right? And let's see this. So here, remember one more thing. For this, VTH is positive. For this, VTH is negative. This is another point. So then consider this circuit, okay, as shown here, right? So here what we have done, the bottom part, that is this part, this is the normal NMOS, all right? On top of which the load, which was earlier resistive load, we have replaced that resistive load by this. So this is what? This is an enhancement mode, sorry, this is an depletion mode of MOSFET, right? And how have we connected this? This we have to be careful. See, this is the gate terminal. Now gate terminal is been connected with the source terminal, shorted. Then what is the VGS? What is VGS for this?
0.
0. So we have set this VGS voltage to be equal to 0, right? And okay. So as soon as we have shorted this point and this point, so among these many characteristics, right? These many, wait. So among is happening, it is going back and back. Yeah. So among these many characteristics, which one we should look into? The top one, right? Vg is equal to 0. So basically, we should be now be only considering this. We should now only be considering this, right? Right. Okay. So, for example, if you can see it here, right? So here also a couple of lines has been drawn. Say this is for Vg equal to 0 volt. Then we should be focusing only for this, right? So this is for ML. So again, we are saying ML is for the load and MD is the driver. So this is load. So this is driver. So it is ML. This is driver. So for ML, we should only consider this. Consider this as VGS load is equal to 0. Right? Okay. Now we have to also plot these characteristics on the same characteristics on top of these characteristics, right? ID VDS characteristics in order to get the voltage output characteristics or this voltage transfer characteristics VTC. So how we can take this characteristics here and plot it here?
Mirror it and shift it by VDD.
Right. It's the same thing, right? Because you see, for this is VDS, right? And for this is the VDS. This VDS is nothing but, okay, for this transistor, VDS is nothing but V out, right? So, and here we can also write that V out is equal to VDD minus VDS load, right? Isn't it? So if you want to take these characteristics and put it here, so what we have to do, we have to just put it like make it inverse, right? So make it a mirror image and shift it by VDD, right? So this is VDD, say this is VDD, right? Then the characteristics, these characteristics, we can probably do it. 1 minute, which way? And say this is the current and maybe then looks like this. Right, like this, right? You understood, right? So here is this 0. So if you see this equation, what we are doing, if we want to put or plot these characteristics on top of these characteristics, then what is the relation? This relation you consider here, this V out equal to VDD minus VDSL. So you have to substitute this each and every value from this, right? For example, for 0 value, if you put it here VDSL equal to 0, so that means V out would be equal to VDD, So this point would come here VDD, right? So here say this is at say 0.2 volt, right? So this is at 0.2 volt, then it is say 5 volt. So 5 minus 0.2, it is 4.8. So 4.8 would be here. So it would be here, right? It's like that if you come here. So this is 5 volt. So it is 5 minus 5. So it is 0. So that 5 volt would come here, right? So this point would be plotted here. So like that you can make a mirror and plot it here. Okay. So here we have to see now the intersections. So where are the intersections? This point, this point, this point. Okay, maybe I can take the green one because see here you can see earlier dots, right? This earlier dots, because you know this I have drawn it once and keep on copying this one. So this is for the resistive load only. Okay, so that's why you can see these points here, but do not consider this. Huh? So this is the point. This is the point. This is the point. So after that, where will be the next intersection? After this, where will be the next intersection?
In the triode region.
triode
In the triode region directly, right? Then here, right? So you can obviously see from here, unlike other cases, you know, you remember other cases for resistivity is like this, right? The change was type of change in output voltage was type of linear, like mostly linear, right? But here you see from here to here, it changes, the output changes very small. The change in output is very small. But from here to here, the change in output is all of a sudden, right? So that fall, okay, from the from the rising part to the falling part, that will be quite sharp, right? I hope you are understanding what I'm trying to say, right? Okay, so now this triode region, then if you have increased it even more, VG, then it will be the triode region. So here, what I'm trying to say now, maybe I can even break it into smaller sections. Say this is at say what voltage we have taken here. Okay, 0.5. Okay, so say this is for 0.5 plus volt, right? VG. Then you further increase it to 1 volt. Okay, 1 volt, right? Then the intersection is this. Then you see like 1.5 volt is this. Then you see 2 volt it is. Then you see 2.5 volt, right? This is say 3 volt. And say you can have like still some few more lines on top of this, right? So you can see what I'm trying to say is that from 2 volt, when you increase it to 2.5 volt, the output voltage, see earlier the output voltage was this much, right? This is 0 from here till this much, right? And all of a sudden, when you are changing this input voltage from 2 to 2.5 volt, the output voltage is changing from this much to this much, right? This much. So you can see we change in for this region, this is the transition region, the change in output voltage will be quite significant, and that's also quite easy to understand graphically, right? Unlike the earlier cases where the change is type of linear here, right? So one obvious advantage you have noticed if you have used here one depletion mode MOSFET in this fashion, right? Okay, then could you please help me out here in this section to draw the voltage transfer characteristics? Okay, so let me see that who can help me. Say we are increasing the V in voltage. Please tell me what is happening in each and every step. Who want to volunteer? Akshay, would you like to?
For V in equals to 0, V out will be VDD.
For V in equal to 0, V out would be equal to VDD. Very good. Okay. Then
Then it will have a small decrease by very small
it
amount.
will have a small decrease. Really think carefully and then tell. Anuj, would you like to try?
So the dots are actually shifting towards the left side, so it should have a
Hmm,
decrease.
But what about the threshold voltage? Okay, until and unless you have not switched it on, right? So your output voltage will be fixed at VDD only, na?
Yes, sir. Initially it will be fixed.
Fixed, right? So say this is the threshold voltage, VTH driver. So until and unless you are crossing the threshold voltage of the driver, your output voltage is going to be fixed at VDD. Okay, then what will happen?
So after that it will fall.
After that, definitely it will fall. So
Because small V change, there is a high current change.
not really. So now, till now, means till this region, we are still at this point, right? Right?
Yes.
Till this region, we are still in this point, no?
Yes.
Right. Okay. So after that, we are changing VG. That means we are changing this one, right? So we are still in this region. So here you can see, as we are increasing this VG or input voltage, the change in output voltage is not that way significant,
Okay, sir.
isn't it? So it would be something like this, right? So after that, once you have crossed this, right? Once you have come to this region, so here the change will be quite rapid. Right? Now, once you have reached to this, then after that, change in output voltage. Change in output voltage is basically, this is the output voltage axis, right? Again, it will slow down, right? Again, it will slow down. Now, who can comment what would be the value of VOL dash? Can it reach to 0?
No, sir.
It can't, right? Because again, the same thing you can see here. If you have one more, suppose if you have considered one more line, okay, for another higher VG, then still also your output voltage is this much only, right? It is this much only, right? It is not going to 0. So output voltage, the minimum output voltage again here cannot be equal to 0. Right? I hope this part is clear to you. Okay, if this part is clear, then let us divide this total VTC into a couple of regions. One is this region, one is this region, and the other one is this region. So region 1, 2, 3, and 4. Okay, and let us see. So in region 1, please tell me which transistor is in which mode. So this is MD, so that is a driver transistor. This is ML, load transistor. Yeah. So in region 1, transistor MD,
Cut off.
cut
So
off.
cut off.
ML in triode region.
This is in triode region. Okay, next. Region 2.
Saturation and triode.
Saturation and triode.
Very good. Region 3. Region 3.
Both in saturation.
Very good, Alicia. Region 4.
Triode and saturation.
Right. Triode and saturation. No, so why we are writing this? And is it really make any sense to write, to understand why this are? Yes, this makes sense because now if I ask you some numerical question, okay, or some analytical one, right, to find, what will be the slope in this region, or to find what would be this point, right, VIL, what would be the VIH, right? So for that, you should be able to find the output versus input relation, right? V output versus V input relation, right? And for that, you should know that which transistor at that moment is operating in which region, isn't it? So you should know which transistor would be operating in which region. Then only you can identify it and you can do it. Right. Okay. Now I have a question here. So probably we will not discuss the analytical part here. But if I ask you that what would be the current voltage relationship, what would be the current voltage relation for this type of MOSFET? Current voltage relation means that ID equal to the expression of ID actually. That how it is related with the gate voltage and drain voltage. So can anyone guess what would be the current voltage relation for this type of transistor? Ranbir? Ranbir, can you hear me? Ranbir Singh?
Yes, sir.
Yeah, Ranbir, can you guess? Like what should be the current voltage relation for this?
It would be similar to like the enhancement type.
Similar to that only. Then what would be the only difference? Only when you are putting the threshold voltage, you have to take care of the values, right? Threshold voltage values.
Yes.
Right? Very good. So it would be similar to that of E mode transistor, right? So now if I ask you to find what would be the slope in this particular region, then please don't tell that we have not discussed in this in class, right? Because we are not doing, because it's type of repetitive thing, right? If you understand the thing here, the basic thing, equations are same, just do the same thing, make both, write the equations for saturation region for both this transistor and this transistor, equate the current, and that will basically give you the V output versus V input relation, and from there make the dV out by dV in, and that will give you the slope. Right? So we are not doing this thing again and again. It's a type of repetitive. If there is something new, obviously we will do that. Fine. Okay. So I hope that in this regard, if some numerical question been asked, you will be able to solve it. Okay. Is there any doubt regarding this NMOS inverter with a depletion load? Okay. If there is not any doubt, then probably we can jump into this section. Okay, which is type of recap of all these type of inverters that we have learned. The first one starting with resistive load, right? So here you can see this is the resistive load part, with enhancement load, which we have discussed I think yesterday. So this is that enhancement load, and with depletion load, right, which we have discussed today, and you can see the depletion load here, right? Okay. So let us take one by one and try to analyze their performance, okay, or requirements in terms of area, VOH dash, VOL dash, static power dissipation, and all this stuff. Okay, so what about area? As you know, here you need R, resistance, takes very large area. Right? What about enhancement load? Area requirement is low, right? For depletion mode, again, it is on transistor only, so area requirement is low, right? Okay, what about VOH dash for this? Yeah,
VDD.
yeah, very good, VDD. What about for this?
VDD minus VTHL.
Very good, VDD minus VTH.
L.
VTH
Load.
L or D?
L.
Ranbir,
So L.
this was
Load,
L.
load,
Load.
L. Okay, load. Okay, and for this?
VDD.
VDD. See here, we have done this, na? Today only, VDD. Okay, what is VOL dash? VOL dash for this means I am definitely not asking the value. Is it 0 or not 0?
Non-zero.
Not
So
0, right?
VDS saturation.
What VDS saturation? But that is not a correct way to say that VDS saturation, because
Okay,
VDS
understood.
saturation is dependent again on the VG,
Okay.
right? Right. So it's basically, we can say like it is greater than 0, right? We can say it like that. What about for this? What about here?
Greater than 0.
It is 0.
Greater than 0.
Greater
Greater
than
than
It
0.
is also greater than. It is also not equal to 0. What about for this depletion load?
Greater than 0.
Greater than 0. Okay, so you can see on VOL dash, like for all all three of them, okay, are not performing well, right? So from this type of enhancement load is worse, because here this the VOH dash, even that is also one threshold voltage lower. Okay, now let us comment on the static power dissipation. Will there be any static power dissipation for this?
Yes. Yes.
Yes,
sir.
because when you give give here logic 1, transistor 1, direct connection between the VDD and ground. So here it is, yes, static power dissipation. What about this? What
Yes.
about this? Yes.
Yes.
What about this? Yes. Right. So for all three, you can see the static power dissipation is an issue. Right. Because for all three, if you have given here 1, then also you can, this is already on. So you can see there is a direct path between this. So that gives rise to this static power dissipation. So we have to think, from this perspective, that we do not want the static power dissipation, right? For example, I do not know whether you have, I have given you one, homework if you have done that. But if you see this, suppose this is using that enhancement load, right? So for this inverter, the power dissipation is 2.11 milliwatt. So for one inverter, it is 2.11 milliwatt, right? Now think about it in a practical IC, how many transistors would be there? Say 1 billion, say 1 billion. So multiply this power with that number. Then can you just guess what would be the total power dissipation by the IC? So what will be the situation of this IC? Means it will be like red hot, right? So hot that it will even eventually burn out, right? Because power dissipation, it will dissipate as a heat only, na? Right? So the IC will become so hot that it is like practically it is not been usable, right? And also you remember one more thing which we will also need to keep in your mind, is that heating plays a very important role in semiconductor devices. For example, mobility depends quite extensively on the temperature, right? So if your temperature of the IC is rising, right, then what is the current that you are expecting, right, at room temperature? And suppose at room temperature you have calculated current of 1 milliamp, right? Maybe at the elevated temperature that may reduce to 0.2 milliamps. So it can significantly reduce. So your entire circuit will fail then, right? So you have to keep that thing also. What is the region of temperature tolerance that you have considered during your design, and you have to mention it, that this circuit can be used for this temperature only. Now, when you are seeing this temperature only, it means the external ambient temperature is important. At the same time, you have to also consider what is the power dissipation, and due to the power dissipation, what would be the rise in the temperature due to the power dissipation in the IC itself, right? All these things you have to take care. So you understand this thing, that if we need some practical digital IC, then we have to reduce the static power dissipation. There is no other way, right? So our next goal would be to reduce how to see or to look forward, so that we could be able to reduce this static power dissipation in a digital IC. And for when we are seeing digital IC, we so far we are discussing only the inverter circuit, so we'll stick to the inverter circuit only. And if for inverter circuit it holds, we should be able to do it for the other logic gates as well. And digital IC is made up with the logic gates only, right? So let us stick with the inverter circuit only. Okay. Okay, so yeah, but I forgot one thing. But before we go to that place, means we go to that one where we can think of doing the reducing, we can think about the static power dissipation, that issue, right? But before that, let us consider one more thing. Okay, say this is what? This is an inverter gate, right? Inverter gate in which technology? Inverter gate using NMOS, and this is NMOS, and this is depletion load, right? NMOS depletion mode inverter, right? So this is the difference. Suppose this is the reference technology. Then it has been asked here that you have to design a 2-input NAND gate and NOR gate using this technology. So can you please do it? How can you design 2-input NAND gate and NOR gate using this technology? Let's see who can answer this.
Sir, for NAND, we keep the two loads in series.
We keep the two load series. Okay, what about two loads in series? Means load is here, this one.
Sorry, sir, the two drivers in series.
Two driver in series. What about the load? Tarun, what about the load?
I think there is no change necessary for load.
There is necessary change in load, right? So are you suggesting then something like this? Say this is V in 1, this is V in 2, this is ground, this is V out, and are you suggesting something like this?
Yes, sir.
Okay, and why do you think this will work?
So because for NAND, when both the inputs are 1, then
Right.
only the output is 0.
Right. So when both inputs are like 1, 1, right? Then you can see there is then if you consider the capacitor, load capacitor here, then load capacitor get a path to discharge and make this voltage to from VDD to 0. Am I right? Right. Say for any other combination, say for 1, 0, right? One of the transistor would be off, so this path is broken, so the output would be high only, right? And you are right. So for load, this only one this depletion mode transistor would be enough. Okay. Then can anyone else tell me what about the NOR gate?
They would be parallel.
They will be parallel. Very good. NAND gate, they would be in parallel. So this is V in 2, this is V in 1. Okay, that's great. This is NOR. Okay, so here the difference is this one, right? Fine. But I could have also given the difference something like this. The reference inverter. Oh. Then in that case, I hope you will be also able to do this NAND gate, NOR gate, AND gate, OR gate, right? Can you? I need your confidence that yeah, you would be able to.
Sir,
Yes.
sir, can you please explain how this NOR gate works?
How this NOR gate works? Yeah,
No, sir,
sure.
I know the truth table,
Uh-huh.
but here how it, like, how do we get that behavior?
Okay. So then please tell me one thing here. V in 1, V in 2, V out. Okay. Just I need your. Yeah, please tell me what would be the expected output for this case. 0, 0
One
from the
zero
truth
zero
table.
zero.
Huh?
1000.
1, 0, 0, 0. Okay. So when both input are equal to 0, then only output expected to be 1, right? Okay. Let's see this from here. So always consider this load is the CL, right? The capacitive load, right? Okay. Now let's discuss one by one. Let's take, okay, first discuss this thing, okay? Like this combinations, say 0, 1, okay? So when you have 0, 1 combination, this transistor is off, but this transistor is on, right? So if this transistor is on, so whatever is the voltage that gets a path to discharge to the ground. So that way, this CL value will drop to 0, right?
Okay, sir, I get it. I understood.
You understood? So
Yes, sir.
from here, it is like this.
Yes, sir.
Okay. So then, so far, if any technology is given to you, please tell me that you would be able to design any gate in any of this technology. Please tell me, like, if you are confident, then we can move. Otherwise, if you have any doubt, you can stop me and tell me. I can discuss and then move forward.
Yes, sir.
Okay, very good. Okay, so we are stopping our discussion so far here. But only thing is that remember that static power dissipation is a big challenge and we need to address that static power dissipation, right? Okay. So we are going to solve that. Okay. So again, as I mentioned, like we will stick to the inverter circuit only. So this is an inverter circuit, you know, what this is the general from our basic understanding, okay, or general, you can say the block diagram of an inverter circuit, right? So here we have the input, here we have the pull up network. It is called this PUN in short. It is the pull down network. It is called PDN. This is the load capacitor right here. So why pull up network? Because during when this capacitor has to charge, it has to charge through this. That means the capacitor voltage can rise from 0 to 1. So that is called the pull up. Why pull down? When this part is on, right? Then the capacitor will discharge through this, and that way the output voltage will drop from logic 1 or from VDD to 0. Okay, or from logic 1 to 0. Right? That's how it is, why it is called the pull down network and pull up network, right? And so far, as of our discussions, like this we have considered the load, this is considered the driver, but it can happen that the input is not only driving this lower part. It can happen the input can drive as well as this one. No harm in this, right? We can connect this input to both pull up network and pull down network. So far we do not need, because if you see the earlier techniques, so here is the resistor, so no need of any input. Here the input gate input is already connected, shorted with here. Here this input is already connected with here. So we do not have any requirement of connecting this input to the top load or the pull up network. But if there is any requirement or from any design point of view, then we are free to do that. Okay. Okay. Right. So you understand, I hope, from this part that a pull up network and pull down network, and this is the general block diagram, right? Now we have to carefully choose that what can we take use for this pull up network and what can we choose for this pull down network. Okay. Remember, our goal is to minimize the steady state power dissipation, right? That was the goal with which we have started this discussion. Now, again, as you can see from here, as I have written here, so how can you minimize the static power dissipation? Suppose if you can choose your pull up and pull down network such that during charging or during when the capacitor is getting charged, so that means the capacitor voltage is rising from 0 to VDD, right? During this time, if the pull down network is open, then there is no direct path from VDD to ground. No static power dissipation, path is not complete. The power is only being used to charge the capacitor, right? Okay. So that means this is rising from 0 to VDD. So that means what we have given means what is the input here? The input is at logic 0, right? So if input when you have given input logic 0, then pull up network should be on, pull down network should be completely disconnected or open, right? Then this thing can happen. Okay. So the other case would be when you have this input as 1, then the pull up network would be completely open. It will not conduct any current, but the pull down network would be completely on, so that the capacitor charge, the stored charge, can be discharged through this pull down network. So here you can see two in steady state input case, means the input 0 or input 1. In both cases, the VDD is not directly connected with the ground. So in both cases, there would be no static power dissipation. So far, again, you can say this is not a, you are saying in terms of block diagram. Yeah, try to understand it from the block diagram point of view. Then obviously we can go to the, see that which component of circuit or components of circuit we can use for pull up network and pulled out network to satisfy our requirement, right? What is the big deal in that? First, let us understand from the block diagram point of view only. So here it is getting discharged, means discharge from VDD to 0. Okay. Here, one thing you should notice that during this discharge, right, there is a finite time delay between this, right, VDD to this, because this is one capacitor through and it is discharging through this pull down network. So you can consider it to an equivalent resistance is there. So RC time delay would be there. So there will be a time delay, right? Similarly, when it is rising from here to till here, right, there is also one delay, right? So this is another delay which we need to take care. Okay, but so far, means as of now, the delay is not the primary concern of our discussion. The primary concern is to reduce the static power dissipation. But I just wanted to discuss this thing and point it out that here is a delay component, both when the rising part and when the falling part. Okay. Okay, then just think about it. What component probably we can use as a pull up network and pull down network so that this particular criteria is being satisfied. Okay. Okay, so I think it's already 11. So what we will do, we will just take a small 1 or 2 minutes break. Okay, and then come back and start with and see that what are the components actually which can help us to achieve this criteria. Okay, so I will stop recording here so that we have an 1 hour recording this and 1 more hour recording for the next class. Okay. Okay, so I'll be back in 1 or 2 minutes. Okay, drink some water and come back. Maybe if you want to do the same, so please feel free to do.